So today's lecture, I'm going to review the last 6 lectures, which are essentially from the chapter 4 of my book, Engineering Optimization. And this chapter is titled Newtonian Methods. And I'm Dr. Ranjan Ganguly. Now, essentially, this chapter started with the Newton method. And this is a very classical method which uses the Hessian matrix to find the descent direction. And we showed that the requirement of positive definiteness was placed on the H matrix to ensure that this search direction is a descent direction and satisfied the descent condition. Now the classical Newton method uses a unit step size during the search, and we can enhance this method by creating a one-dimensional search, and this would yield the modified Newton method. Now we saw that the Newton method shows quadratic convergence, but the problem with the Newton method is that it's somewhat impractical for real-world problems because the calculation of the Hessian matrix can be very computationally expensive. And this problem gets more difficult in real-world situations where you have a large computer simulation program which is used to calculate the derivatives using some finite difference method, and therefore the Hessian calculation would involve an enormous number of function calculations which would be very cumbersome with most computer simulation codes. Now the extension of this Newton method to the Marquardt method was proposed, and the Marquardt method essentially tries to combine two methods, which is the Newton method and the steepest descent method. The steepest descent method is also known as the Cauchy method in some of the mathematically inclined literature. And here what happens is that you use the fact that D is minus C as the search direction. So the Marquardt method essentially uses the steepest descent search direction when you are far away from the minimum point, and it slowly morphs into the Newton method when you get close to the minimum point. Recall that near the minimum point, the H matrix is likely to be positive definite, and therefore it is going to yield a good search direction for you. Very far away from the minimum point, the negative of the gradient is going to be a very good search direction. So of course the Marquardt method is not very practical because it has the same ills about using the H matrix and so on, and it also tends to use a very small step size when you are very far away from the minimum point, because the step size is essentially controlled by that parameter lambda. But the reason why the Marquardt method is often taught in textbooks is that it gives you a preview for the quasi-Newton methods. Now in the quasi-Newton methods, you typically try to resolve the problem about calculating the H matrix by essentially building up this H matrix using information about change in gradients and change in design. Now the change in gradient is the change in the vector between ck plus 1 and ck, and the change in design is the change between the vectors xk plus 1 and xk. So this information is there typically with you at each point k, and therefore the quasi-Newton method essentially builds up H matrix during this time. Now all these quasi-Newton methods come from a certain philosophy which satisfies the second condition, and the descent direction in these methods must satisfy the second condition. We also showed that the quasi-Newton methods can be thought of as multidimensional extensions of the second method. We see how the Newton method for 1D problem can be expressed as a second method if we take certain finite difference approximation of the second derivative. And essentially what we do is we get rid of the second derivative by using this finite difference approximation. In a similar way, the quasi-Newton methods get rid of the problem of calculating h by using a kind of finite differencing at a multidimensional level, which is clear through the second condition in the multidimensional problem. Now we also saw that the BFGS and DFP methods are the most powerful and widely used quasi-Newton methods, and these essentially try to reconstruct the matrices H and inverse of H respectively. Now the point about using H is that to get the search direction you have to solve a linear system. However, in the DFP method you have to solve a multiplicative system, or essentially the search direction can be obtained by multiplying a matrix with a vector. So in certain cases the DFP method may be more computationally fast. Now both these methods typically start out with an estimate of H as the matrix I, which is the diagonal matrix with all unit components in the diagonal. And essentially whenever you use this I matrix for H, you are essentially going to the steepest descent or the Cauchy search direction. So very similar to the Marquardt method, here you are starting out with a steepest descent type of method when H is equal to I, and you are progressively building up the H matrix, and very near the final minimum point you should be able to reconstruct the H matrix quite well for most problems. And for quadratic problems you should get back the H matrix. So in my book I have given a couple of examples where this is the case. Now most theoreticians like the BFGS method more because it generally tends to be better in terms of numerical behavior and is also robust to problems in the line search. So one of the things we have seen is that a very precise one-dimensional line search can take a lot of computer time, and the BFGS method is somewhat good in that aspect. If you recall, the conjugate gradient methods do require good line searches in most cases, especially the Fletcher-Reeves method. Of course, the DFP method would yield certain computational benefits because of its relative speed compared to the BFGS method, because you don't need to solve a linear system for the DFP method. We also saw the enormous importance of numerical derivatives when it comes to optimization. Now, in contrast to most of the material you see in textbooks, you really don't have simplistic functions to differentiate in most real-world applications of optimization. The value of the functions come from computer codes, and therefore you need to calculate finite difference derivatives. Now we saw that once we want to calculate finite difference derivatives, the problem of step size selection becomes very important. And this essentially is a trade-off between round off and truncation. Now truncation comes from the fact that when we expand the Taylor series expansion and create the finite difference formulas, we tend to neglect many terms in the Taylor series. And truncation can be brought down by selecting very small values of H, the step size. However, round off comes from the fact that computers have finite precision mathematics, and essentially this may be 10 to the power minus 8, 10 to the power minus 16 and so on. But what happens in computer programs is that essentially when you see a very small number, beyond a certain level of smallness, these numbers become same as far as the computer is concerned. So you are also performing calculations of subtracting two very small numbers when you have situations of f(x) plus h minus f of x. So that's something to keep in mind, and there are certain ways to proceed with relative rapidity in these problems by choosing the step size. So we suggested a possible use of the root of the precision as the step size. Now, central difference formulas will give you better results in terms of reduced truncation. But the problem is you need to calculate one more function here. So central difference method would require you to calculate fx plus h and also fx minus h. And that would require more computer time compared to the forward difference method where you need to calculate fx plus h. And you should have fx normally at your current point. Now, beyond central differencing and finite differencing, the concept of AD was there, and here typically you create a new computer program for derivative calculation using a program which you have for function calculation. And this method will let you calculate derivatives which are of high quality, and typically it is recommended that you download some software package which helps you do this. Of course, if you are a student who is working on this as a research problem, then it may be different. But there are packages such as Tapinade, which you can download. You can subject your computer program to this particular package, and it will create a new program which essentially calculates the derivatives you are interested in. So this is a method which is possible to use if you have access to a program. Maybe you have written a computer program as a graduate student, or somebody working in a small company or startup, and in that case this kind of software may be useful. Now a similar method, but which requires more work from the person doing this process, is to calculate the gradients as an integral part of the computer program. Now when you typically create a computer program for solving any physical system, you have certain lines of code generating, for example, the mass, stiffness matrix and so on for a structural system. And somewhere you will have some lower level functions where you have explicit coding of the different parts of the matrix or the vectors. So this particular coding would be explicitly there in terms of shape functions, the stiffness of the structure, the density, and so on, cross-sectional properties sometimes, etc. So what you can do is you can use chain rule differentiation, differentiate the various matrices and vectors of your problem, and try to express your objective function derivative in a closed form. And when you do that, you can code this into your computer program as part of the solution process. So let us say you have written a computer program which gives you displacement, stresses, strains, frequencies for a structure. Then you simultaneously add in the material which gives you the derivatives of these particular values with respect to the design variables. Here the design variables may be the structural and mass properties of the structure. Now this kind of method is extremely good and time saving in case you have domain knowledge about the system, but you would be required to make changes inside the computer program. And this is easy for a graduate student if you are an expert in the area and you have written some code. And maybe by using this kind of derivative information in your formulation, you can solve various intractable problems which would be not possible to solve if you resorted to finite differencing and so on. For example, once we were doing a problem of stability maximization, and the stability max problem was coming at the end of a process which involved solving for frequencies, doing a trim solution for a rotor, and then solving the stability matrix using Floquet theory, which was all very time consuming. But because we coded in the sensitivity derivatives as part of the computer program, we had access to this high quality stability derivatives, and therefore gradient based optimizers can be used to solve this problem. So this is something which you can consider, especially if you are a graduate student and you are looking to use optimization to discover something very interesting. Maybe you are interested in a robust or reliability design problem where you need to make an enormous number of calls to the function because your optimization loop is outside a Monte Carlo loop for the particular problem. So this can happen because some of the objective functions which you are using in robust and reliability based design are actually statistical in nature. So instead of, let us say, maximizing the frequency or minimizing the vibration, you may want to minimize the vibration as well as the standard deviation of the vibration. So in those cases, any such method where gradients are much cheaper becomes much more better, and it is certainly useful to use it. So this ends our chapter 4, and in the next class we are going to start with the constraint optimization methods, and I'll see you in my next video.